Hi everyone. So last time we discussed discrete state space paradigms for dynamical systems, and in particular discrete space in continuous time and discrete space in discrete time. So now we're going to focus on continuous space in discrete time. And one major difference here is that the transition probabilities from state to state will no longer be drawn from a categorical distribution, but instead will be drawn from sort of some continuous probability, the states that you're evolving to will be drawn from continuous probability densities. So let's go ahead and write out our initial conditions, or initialization rule, I should say. So this is called just like it was before for the discrete state paradigm, the initialization rule. And this here is going to be my transition rule. And the Q here will be the probability distribution, which has a coinciding probability density, which typically I would write out as Q sub n, and then Rn plus 1 conditioned on Rn. So now at this point we have a probability density describing how I get from some state to some other states. So let's be a little bit concrete in terms of sort of the meaning of this and this for just a second. So initialization and transition rules. So when I write out rho of r dr, this is the density coinciding with my probability distribution R1. So the way I interpret this here is to simply say that this is the probability of starting some dr near R. Now what about the density, the transition density? So let's go ahead and write that down just underneath. Oops, right here. So Qn of R, or R given R prime dr, is equal to, or how do I interpret that? It is the probability of jumping from R prime to some dr near R. In other words, what we're doing is we are describing sort of a transition density in going from some very specific R prime to some general region dr around R. So completely different from what we've seen with discrete states. In discrete states, we had seen sort of transition densities, which were categorical distributions, where we can go to a bunch of discrete options as our states. Here, our states form a continuum, right? So in principle, you can start off from some R prime, and then go to some region dr around some final position R, a continuum of different sort of positions. Now, what we'll be doing is we'll be turning to a very specific example of going from some R prime to some R, except we will follow sort of Newton's equations. So in some sense, F equals ma to get from our initial condition to the final position. Now you may say that's not very interesting. In this particular case, I know exactly where I'm going, so the final position will not be distributed. I know exactly what the R is going to be if I propagate according to F is equal to ma. That's true, but let's start off with a simple example and then do something complicated next. So let's talk about modeling. EOMs. And EOMs is kind of shorthand for equations of motion. So, the simple equations of motion for Newton are that dq equals p over m dt. I'll write it down and then I'll explain it in a word. And dp equals f of t times t. And here we're assuming for simplicity that the force, for now, is independent of the state of the system. So this equation here is none other than F is equal to ma. There's the F. If I move the dt over onto the other side, I have the change in momentum. That's mass times acceleration. Similarly here, this is basically the equation describing the momentum. So the change in position multiplied by mass is the momentum. So maybe we're more familiar with these equations written down as follows, where the dot notation here implies dq dt. And similarly for this equation here, maybe we're more familiar with seeing it as p dot equals f, or more often mq double dot equals f, where I use the fact that mq dot equals p. In other words, I used this very first equation here to fill in or to expand upon this first equation to get the second equation. Either way, we're going to be starting off with equation 1 and equation 2. Those describe how my position changes. Now, when I'm evolving according to Newton's equations, if my position starts off here, or my state, I should say, starts off with some q and some p, I evolve at some point later, let's call this n, and depending on what the forces are, I end up at a very specific point in the future, which we'll call qn plus 1, pn plus 1. And depending on what my forces are at some point in the future, I might end up at another very specific point, qn plus 2, pn plus 2. So in some sense, my transition probabilities, we can already tell that something bringing me from state n plus 1, pn plus 1, given my qn and my pn, is that transition probability, let's call it that q that we had mentioned earlier, will probably be a delta function. Probably be a delta function. Why is that? Because again, there's no uncertainty as to where I go. Given where I started from, I know exactly where I'm going because all I do is propagate Newton's equations to a very specific point. So we'll start off with kind of a little bit of this maybe trivial case or exaggerated case where we're kind of propagating deterministically. And shortly, we will consider examples where we propagate according to Newton's equations, but maybe with noise added. And then we start off with some qn, pn as our state, and then we evolve maybe to potentially a group of, a volume which is acceptable with some probability. Right? So it doesn't need to be a specific point by the time we've added sort of noise to our dynamical equations. I'm jumping a little bit ahead. So for now, let's just use Newton's equations to write down precisely, or I should say approximately already, what the qn will be. So if I start off with q dot equals p over m, I know that I can already integrate this equation, and I'm going to call the equation the following. Whoops. Q t double prime equals q of t prime plus the integral from t prime to t double prime d tau p of tau over m. So the t prime, the t double prime, and the tau in some sense, are a little bit dummy. T prime is my initial condition, T double prime is where I evolve to, and the tau is just my integration variable here. Now, if I integrate my momentum equation, so let's go ahead and write down what that would be. That would be P dot equals F of T. If I integrate my momentum equation, I get P tau equals Pt prime plus T prime to tau d tau prime F of tau prime. So what have I done here? Again, T prime is my initial condition. Tau prime is a dummy variable, and I'm integrating from tau prime to some tau. But now that I have a P of tau, I can plug it in here to figure out how my Q of T depends on my force. Because right now my Q of T, or T double prime, depends on my P of tau, and I'd like to be able to sort of figure that out. So if I plug star into, this point here, then I should get, let's clear this a little bit because it's getting messy, Q of T double prime equals Q of T prime plus the integral T prime to T double prime. I'm looking at my notes here because the primes are hard to sort of keep track of. And then T prime to tau d tau prime F of tau prime, close bracket. So this is kind of one long equation. My final position is equal to my initial position plus this integral. Interesting, I'm integrating over the initial condition. So this integral I will immediately rewrite as T double prime minus T prime, and maybe over M, P of T prime. And then finally I have this expression here, so plus 1 over M, integral T prime to T double prime d tau times the integral T prime to tau d tau prime F of tau prime. And let me make sure everything is correct, which I think it is. Good. So our position at a later time point is given by the initial position multiplied by the time elapsed and the initial momentum multiplied by sort of the integration of force, sort of the integration of over the force over some period of time gives me that momentum, and then I have to integrate or something proportional, and then I have to integrate that once more in order to get the contribution of the force to the position at some later time. Okay. Now there's a couple of things that we can do in order to simplify our lives. The first thing we can do is to sort of appreciate the fact that if we assume that F does not change very much in time, then we can make some approximations. In other words, if F is assumed sort of constant, then we will immediately simplify these expressions to the following. So let me go ahead and write this out. So I have Q of n plus 1 equals Q of n. So at this point now I'm going to discretize time and call my double prime as n plus 1 equals Qn plus now Tn plus 1 minus Tn multiplied by Pn over m plus 1 over m Tn to Tn plus 1 d tau, T sub n plus 1 from Tn to Tn plus 1 d tau, and then I have another integral Tn tau dt prime F of T prime. And then I have 1 for momentum in discrete time, so Pn plus 1 equals Pn plus the integral Tn to Tn plus 1 of d tau F of tau. Great. Now, if my force does not change appreciably over this time period, then in principle I can approximate this term as Tn plus 1 minus Tn multiplied by f, and now I have some sort of choice. I can either evaluate f at Tn or f at Tn plus 1, but since we said it doesn't make much of a difference because we said f is roughly constant, then I'm going to select f of Tn. And finally, we will assume that since this first term here scales as delta t, right, the change sort of in time between Tn plus 1 and Tn, and maybe that delta t is small, so I'm integrating my equation of motion over very small time integrals, then what I find here is that this term is actually delta t squared. If I assume that force is independent, roughly independent of time, then these two integrals here give me a term which is proportional to delta t squared. So if I assume that my integration time interval, so in other words Tn plus 1 minus Tn, is small, then perhaps with some small amount of approximation I can drop terms that depend on delta t squared and only keep terms that are of order delta t. So let's go ahead and write out these two equations in a way which may seem a little bit more intuitive under those approximations. So Qn is approximately equal to, or Qn plus 1 is approximately equal to Qn plus Tn plus 1 minus Tn multiplied by Pn over m. And Pn plus 1 is approximately equal to Pn plus Tn plus 1 minus Tn times f of Tn. Now, this is kind of this dictates the transition probability from my state in Qn Pn to my state that I evolved to, Qn plus 1, Pn plus 1. So let's actually show that for this very simple example as to how these two here dictate a transition probability. Like I said, it's going to be a bit of a boring transition probability in part because it's deterministic. So knowing where I start from, I know exactly where I go. It's kind of like the transition probability that we saw, for example, for the birth process or the death process. We know in the birth process that we add a member. We know in the death process that we remove a member. Here, we're basically saying we know exactly where we're going given all the forces. So if we were to really nitpick at this and rewrite sort of Newton's equations in a probabilistic way, we would say that the position at time n plus 1, given the previous position and the previous momentum, is drawn from, well, a delta function, which is centered at, well, what's dictated by the equations of motion that I just wrote down, Pn over m. Similarly, this equation of motion, Qn Pn, is drawn from another delta function, Pn plus Tn plus 1 minus Tn f of Tn. So this delta function is centered at a different point than this delta function, but they're both delta functions because the dynamics are deterministic. And so if we were to write out the full transition probability, which will look like Q, P, Q prime, P prime, the full transition probability will simply be the product of these, or the probability density. This is the probability density for the transition. That's going to be that's going to be, Q prime plus Tn plus 1 minus Tn, P prime over m. The argument here is Q, because that's where I'm centered. Or that's I should say, the variable that I'm drawing. This is technically where I'm centered. And then I have delta of P, and this is P prime as the argument of this delta function, plus Tn plus 1 minus Tn f of Tn. So I'm just rewriting these, but I'm making explicit the random variable dependence. There's one thing we need to be a little bit careful about. In the textbook, it's different notation, it's different fonts, so it's not as confusing. But this, just to be clear, is the position at time n. This is the probability density coinciding with this probability distribution. So this one here is a probability density. This is a position. This is a momentum. This is the previous position, the previous momentum. And given the previous position, previous momentum, this is a transition probability describing how I get to the next Q and P. So this and that are different objects, different fonts in the textbook, but arguably very similar in writing. So we can do very similar things as it pertains to spatially dependent forces. We can kind of run through this exercise again, and in principle, under the approximation that we drop the delta t squared term, we can have something here that depends on Qn and Tn if we have a spatially dependent force. So the arguments that I put down here for the very special case that we have a spatially independent force actually generalize quite nicely. And we can do more sophisticated things, for example, if we'd like to be able to keep order delta t squared. But I'd actually like to turn to something a little bit more interesting. So the reason we don't see this written down in physics classes is because it's kind of a notational overkill. Physics or any engineering class or elementary science class where they describe F equals ma, the reason is that it's a bit of a notational overkill because, again, if I know where I'm going, then why do I need to use probabilistic notation? So let's go to the case where we start off with some state, Qn and Pn, and we have some probability of landing maybe at some value, Qn prime, Pn prime, different probability of landing at another value, and different one at some other location and so forth. So we have sort of a continuum of states, Qn prime, Pn prime, that we could potentially land on. That kind of falls outside the scope of F equals ma. That would be the case where we have, for example, some noise in our dynamics. So maybe we're mostly following a trajectory, but maybe imperfectly, and we end up here. Now, the perfect trajectory may have landed us here, but there's some noise, and maybe, it lands us in different locations at the final state. So we land somewhere here as opposed to sort of simply following F equals ma. How do we model something with a little bit of noise? So to start off with, modeling things with a little bit of noise is super helpful in the natural sciences. When we're looking at chemical reactions, catalytic reactions that start occurring, a chain reaction that might start occurring, the initial time of reaction may be different, so therefore the end result or the reaction may be completed at a slightly different time. We may look at, for example, cells dividing. They don't all divide at exactly the same time. So then you sort of, at some later point in time, you ask, how many cells do I have? It's going to be some variable number based on sort of the noise around it, precisely the time at which they divide. Now, arguably, this is an example in discrete state space, but what about continuous space? Well, you could have a particle under the influence of an electric field, but that particle in the meantime is being jostled around by thermal fluctuations in the fluid. And yes, on average, it'll follow the, if it's a charged particle, it may follow the field direction. But, the noise may result in the particle sort of ending up in slightly different locations after a specific amount of time. Needless to say, these things are also used for, these random walks with noise are sort of used to describe all kinds of social phenomena as well, including stock prices and so forth. So it's obviously of value. So let's go ahead and sort of modify our Newton's equations a little bit to integrate the notion of noise. So this again is a restatement of the fact that momentum is mass times position dotted, and in our momentum equation, we will write down f t, maybe that depends on position, q dt, plus, and this will be the important part, the noise. Now, in some sense, C will be related to the strength of the noise, and the dWt, the reason it's called W is because it's, this isn't a quote, this is actually what it's called. It's called a Wiener process. But basically what it is that it's a draw from a normal distribution, and we'll get to it, but with zero mean and standard deviation, that's our sigma, of 1. So what are we doing? We're basically saying that our positions satisfy, the original equation. We haven't touched that, except that we have sort of a deterministic portion to the force, and we have a random kick portion to the force. So the momentum is impacted, or the change in momentum over some interval delta t, is impacted both by the deterministic component as well as some random component. And therefore these changes in momentum ultimately impact the position of a particle. So just right off the bat, I know we've been talking a lot about F equals ma, Newton's equations, and so forth. This class is not meant for physicists, but it's only a way of describing these equations I'm just using these equations as an example to describe applications of the Wiener process. Of course, you can add these to different kinds of equations. They don't need to be for example, Newton's equations per se. We're making it kind of a point to use something which is physically motivated from the natural sciences. But again, if you were unfamiliar with this and this, it's not such a big deal. You don't need to know you don't need to know classical mechanics in order to take this class. So let's discuss this interesting new bit. So what is the Wiener process going to be? I'm integrating from t prime. I'm going to write something down, and then I'll explain it. This is dWt over square root equals xi, and xi is drawn from a normal with zero mean and standard deviation, and therefore variance of 1. What does all this signify? Well, let me write what I wrote down here in a slightly different way, and both of these will be equivalent definitions of the Wiener process, and then let's talk about it. T prime to T double prime, dWt is drawn from a normal distribution with mean 0 and variance T double prime, minus T prime in absolute values. Okay, so let's talk about this and let's talk about that. First, let's talk about this one because it may be more intuitive, and then show why this is equivalent to this here. So, what is the second statement saying? What it's saying is that the integral from T prime to T double prime of the Wiener process. So in other words, if I accumulate all of the noise, all of the kicks from some T prime to some T double prime, I will find that the sum of that noise is drawn from a normal with zero mean. In other words, that noise is not drifting to the right or drifting you to the left. It's just, it has zero mean. However, the variance of the noise is proportional to the time lapse. It's a model. This is not fundamental science. It's something that we can write down that feels reasonable. And why does it feel reasonable? Well, the longer we wait, the bigger the spread in the noise. That kind of makes sense. And the spread is directly related to the time interval elapsed. So this is quite a reasonable model to write down, basically saying that the noise accumulates over time. It's not drifting you left or right. And the variance, the spread of the noise, the variance of the noise, is proportional to T prime in absolute value, the time interval change. So t double prime minus t prime. Now, if the variance is t double prime minus t prime, this implies that the standard deviation is square root of t double prime minus t prime, right? Because the standard deviation is just the square root of the variance. Now let's go back to this original equation. What is this telling us? Well, it's another reformulation. The integral of the noise divided by the variance then must be drawn from a normal distribution, and notice the difference here with a variance of 1 as opposed to having a variance which is proportional to the time interval change. So both of these formulations, this and this, are exactly equivalent. I think that this one here is more intuitive, so oftentimes we will be using this, but in very many textbooks people write something like this down, and it's important just for people to appreciate the fact that in one case the variance is conveniently scaled to 1 for you, and in the other case the variance sort of has units, and it's a quantity proportional to the delta t, and so then we need to be sort of mindful of the fact that this integral here has nothing in the denominator. So with that, I think we've sort of explained the Wiener process, and now we're going to describe sort of how to generalize the equations of motion in the presence of noise, and ultimately write down a transition probability density that's not just going to be a delta function, but that's going to be a little bit more interesting. Thanks.